All right, we're going to do chapter 4, which is transformations. You've gone over transformations before. You don't really do transformations in algebra unless you guys did, because that was on your test in 8th grade. But you do some of this, I think, in pre-algebra. We're going to start with translation. Okay, so 4.1 translation. Translation is a pretty easy concept. I got my tech deck right here. I'm going to translate my tech deck. There we go. That's translation. What did I do? Did I change the shape?
No.
Did I change the side?
No.
Did I flip it?
No.
I just did, level 1 skateboarding, right?
Yeah.
I could even do this way, like grind. That's cool. That's still a translation. But I'm still like keeping it the same. That's translation. Okay, that's all you really need to know. And I just used a tech deck in a mathematical lesson. You're welcome. Where did I get it from? I have no clue. It just appeared on my desk one day.
You probably took it.
No, I didn't. It was a gift. It needs new trucks and it needs new wheels because it doesn't. You can't actually do the fun stuff with it. All right. Anyways, so what we need to know is we need to know some vocabulary on page 156. Like I said, there's a lot. So we're going to go ahead, and I probably should have just paused the video for this. Maybe I'll have like just a demonstration with the tech deck while you write this stuff down. There's a lot of stuff in yellow that we need to get kind of written down. So we need to know what a vector is. And then there's like initial point, terminal point, horizontal, vertical, component form. Okay, there's transformation, image, and pre-image. And then finally, there's translation. So basically, there's a ton of words on 156. Let's get them done.
All
Yeah.
every single yellow thing.
Every single yellow thing. And when you're doing it, you don't have to copy every single thing. Just try to write what it is. Vector is probably a long one. Initial point is not. I would define initial point as starting point. That's a great definition. Terminal point is what? Ending point. Like, I'm not asking you to write sentences and sentences. Okay, horizontal component, I wouldn't write what they have in the book at all. I want you to figure it out. And so I'll give you kind of a different little take, and I've marked all over my page, so we'll see how that is. And we write this stuff down largely so we can read our questions. If we don't understand what the question's asking, we're probably not going to get it right. And even though we don't have a state test in 9th grade or in geometry, it is a very important class for the ACT. And just expanding your vocabulary a little bit is pretty good. And then probably we need transformation. Image and pre-image, so you can understand what I'm saying. And finally, a translation. And we're not going to have to write this many definitions ever again, in this chapter anyways, because this kind of sets up the whole chapter. And so we'll just add a couple more words as we go. And this is not a very long chapter. It's like 3 sections, maybe 4. So we'll probably finish it up Monday and then start studying for your final. All right. So hopefully you got what a vector is. A vector is a quantity that has both direction and magnitude. Okay, that's a funny magnitude basically means size. Has both direction. This pen's running out. I need to get a whole new set. Both direction. Okay. A vector is not normally used in just pure mathematics, because a lot of times when we graph, we don't use terms like vector. Vector is oftentimes used in engineering and physics to indicate something is moving, and then the magnitude is going to be the speed or the force or whatever. This is a direct translation to, of course, anytime you do graphing of any type, that directly translates to either computer programming or to building blueprints, stuff like that. Some things are supposed to move. Like when you design a house, hopefully you don't have direction and magnitude. But when you design a car, it's going to move, and the parts are going to move. Although I have seen someone explained to me the blueprints of a skyscraper. Skyscrapers do move. Bridges do move. They're actually designed to move. There's no way to keep them still. If you try to actually keep a skyscraper still, it would break and tumble to the ground. So they actually sway and move with the wind. You might not be able to see it because they don't move that much, but they do move a little bit. Which if you're motion sensitive, go on top of like a 100-story building, you will feel it kind of move a little bit. If you're not motion sensitive, then you'll be like everybody else and it's just a building. All right, initial point, that's your starting point, said that already. Terminal point, that's your ending point. Okay, me personally, the horizontal component is going to be your x, right? What does it say? It uses that kind of that direction, but it's going to be your x, or it's going to be kind of your line that's on the x line. So they said in your book, I think they did something like this. Well, I don't even like that. It's just basically your x variable when you make your triangle. Your vertical component is your y. In component form of a vector is the horizontal vertical component. So that your line segment, so if you have your line segment P and Q, it's going to look like this. Okay, this is not the same as if it had parentheses. It has, and I exaggerate, what are those even called? They're not parentheses, they are what? Does anybody know what the name of those are? Well, I guess they could be, but they're not. They're actually something different. I don't remember what they're called. I always call them carrots, or I bet you there's a word for them in English. But anyways, they're different than parentheses. This is going to indicate movement. This is not indicating a point. This is going to indicate movement. And so, and I don't know why I wrote P and Q in here. That is not what I meant to do. It's basically going to be your X and your Y, but it's going to be movement on the X and movement on the Y. Okay, and so we'll get to that. All right, transformation, your image. Okay. Well, transformation, what? Is a function that moves or changes your figure in some way. And it produces an image. The original picture is your pre-image. So you start with a pre-image, you transform it, and you get an image. Okay, a translation moves every point in a figure the same distance and the same direction. Doesn't change the shape, doesn't flip it. So basically, Here's my tech deck again. This would be the pre-image. That would be the image. Okay? So you start with your pre-image, you perform your transformation, in this case a translation, and that would be your pre-image. Okay, we got done with all this kind of stuff. We now need to basically go over what we're doing with stuff and things, okay? I'm not going to worry about the other stuff for now, because we did too many definitions as is. Okay. And largely we're going to do this in our computers today, which this might not apply in years to the past because we have working computers. So I'm going to just draw like a little thing here. Okay, so we're going to have a little line here. And we're going to work on doing the component form of this line. Okay. So this is basically my starting point, and this is my ending point, and I want to know what we did with our starting point. Okay. So my starting point, just to help you out, is like 1, 2, 3. It's a -3. And then that would be 2. So these are points, not vectors. My ending point would be a 2, a 2, 6. Okay. And so I need to figure out what I did. So it's going to have two components. It's going to have the x. So we moved it over. So it has distance and magnitude. Direction and magnitude. And then I'm going to do this. So it has direction and magnitude. Now I need to break it down into the vector form. So how far did I go over? Okay, so I'm going to use this. That means I moved x over 5. And it's positive because I moved it. And then I moved it up, so that's also positive. How many up did I move it? Okay, that's your vector. If you can get that, then you're a good way into physics. Yeah?
Isn't this basically rise over run?
It is basically rise over run, but I don't want to confuse you with that because I'm not putting it into a ratio. I'm putting it into this form. Okay? And I like to look at this like, okay, if you have a rocket in space, there's my rocket. It's super awesome. Okay, and I want the rocket to go over here. What do? Can I just like use a steering wheel and fly it over there? The way rockets work is they work in the vector form situation. So I might have an engine here, and I might have smaller engines here and here, because basically you need to apply a force because there's no gravity, right? So you need to apply a force. So to get there, I need to shoot this rocket, some magnitude, and then I need to shoot this rocket some other magnitude to move it this direction, right? So basically that's a direct translation of what it is. So we could calculate, if that was our thing to do, how much energy I need to produce here and how much energy I need to produce here. Would I need to produce any energy here to get here? No. Of course, in space, to stop me here, I would have to produce energy from here and here to undo what I just did. So we don't do that, but you do that in physics, and that's kind of fun. All right. Anyways, let's move on to a different style problem that you're going to have to do. So the next problem we're going to do is basically, I'm going to have a graph, and this is why we're going to do the computer. It's so much easier. I might have something like this. Yay, there's a little, you can't see it, but you can imagine what it's like. It's kind of like my rocket ship. And then I'm going to have this. And I'm going to move it. So how do I move that? Well, I take each point and go 1, 2, 3, 4. And down 2. 1, 2. 1, 2, 3, 4, and down 2. 1, 2. 1, 2, 3, 4, and down 2. Okay, it would help if I did my line straight. But you see how I moved that using this little vector? Okay, so we're moving right along. Okay, so that's vector form. There's another form that you will see, and it will tell you what it wants you to do here, and especially on the computer. So here's the other form, and this is called the component form. So there's vector form and there's component form. And so I'm going to show you the exact component form of this vector here so you can understand the difference. It's pretty tough. I'm being sarcastic, I'm sorry. Okay, can you see the difference between the two? And I did a terrible job with that. That's supposed to be like that. So, let's pretend I did that. So this means to go take your x and just add 4, right? I took my x and added 4. This means to take your y and subtract 2. Can we see how this is exactly the same thing? Okay. So you might have to do this form, you might have to do this form. Okay. Let's go ahead and look in your book, and we're going to look at, and this is exactly why we're using the computer, because it's so much easier to use their graph paper and do it. We're going to look at the book on number 13 on page 160. Okay, do we see that? It says, what is the image? What is the image of A, comma, parentheses 2, 6? Okay, so what is the image? Is the image the first thing or the second thing? Pre-image is first, image is second. And that's why we went over the vocabulary, because to me, I want it to be the image and then like something else, right? Okay, and so basically, I want to know what the pre-image is. Okay. And so, oh no, I'm sorry, this is the pre-image. I want to know what the image is. And so here's what the image is. I'm going to take that little thing up there, and I'm going to do this. So the image is going to be this. And this is also what you do. You call it A, and the pre-image is A. The post-image or the image is going to be A prime. So this is how I do that. 2 minus 8, 6 plus 4. So the image would be what?
-6, +7.
Can I make this hard? Okay, maybe. Let's see. Let's see if I can make this hard. Let's look at 16. It starts with the pre-image, and we know it starts with the pre-image because, no, I'm sorry, it wants the pre-image, it starts with the image. So I need to go backwards. How would I go backwards from the image to the pre-image? Yeah.
Switch to the negative signs.
I just switched the negative signs. So to get from the image to the pre-image, I'm supposed to use this, right? X minus 8, y plus 4. But if I start with the answer and want to get the question, if I start with the image and get the pre-image, you just do this. Opposite. Opposite. Does that make sense? Yeah. You're in good shape then. 12, -7. This is definitely going to feel a lot more math-based than maybe the last chapter. Okay. 2 more definitions, and then we're going to do our work, and I'll explain how that's going to work. Rigid motion and composition. That's a big word. I bet you can find it. It's on page 158. Okay. A rigid motion is a transformation that preserves the length, the angle measurements. And another name for rigid motion is isometry. So basically, it's not going to change the size or the shape. And a composition of transformation is when two or more transformations are combined to form a single transformation. Okay? That's what happens most of the time in real life. So, for example, if I were to move this here and then move it here, that would be a composition of two different transformations, right? I translated it and then I translated it. Okay, there are theorems and postulates, but we don't use them as such, and so I'm just going to leave it as definitions, and that's what I'm going to leave it as.